Welcome back to The Explainer, everyone. Today we are cracking open one of the absolute most brilliant, yet honestly pretty frequently misunderstood brains of modern engineering. We're talking about automation. Whether it's a drone hovering perfectly still in a massive gust of wind, your car's cruise control locking in at exactly 65 on a super hilly highway, or even the complex temperature controls in a giant chemical plant, they all face the exact same problem. How on earth do we make a physical system do exactly what we want when the real world keeps getting in the way? Well, that is exactly where the PID controller comes in.
I want you to really think about this for a second. Can you always trust your commands will be executed accurately? Right? Like, say you have a system, your software issues a command, and you just expect a response. You tell a robot arm, hey, turn X degrees to the right, or a rover, move forward 15 wheel rotations. In a perfectly sterile theoretical universe, the machine just does it, no questions asked. But out there in the real world, the stakes are way too high, and absolute trust in a simple blind command is a luxury we just don't have.
Here's the thing. If you send a dumb command to a machine, like literally just move forward 15 wheel rotations, you're basically banking on a flawless environment. But reality is messy. It's packed with environmental forces constantly pushing you off course. Friction changes beneath the tires, motors start to wear down, the wind blows, payloads shift around. A blind command just isn't going to cut it. The system literally has to be able to observe its own mistakes and correct them on the fly. It needs a smarter controller to wrangle that unpredictable reality.
Okay, let's dive right into this. Here is our roadmap for today. First, we'll look at 1, the control problem. Then 2, anatomy of a PID. From there, 3, measuring system performance. Next, we'll put it to a physical test with 4, the mass spring damper. And we'll wrap it all up with 5, real-world applications. Let's get to it. Starting off with section 1, the control problem. Before we can even start talking about how a PID controller fixes errors, we kind of need to nail down our vocabulary and define what an error actually means in the automation world. It all comes down to this one foundational concept, the set point. The set point is just the desired target value for your system. Think about the thermostat in your house. If you want your living room to be a nice, comfortable 70 degrees Fahrenheit, that's 70 degrees, that is your set point. That's the ultimate goal. Meanwhile, the room's actual current temperature is what we call the measured quantity. So if the room is sitting at 65 degrees, the controller looks at the 65, looks at the 70, and calculates the difference. That difference is the error signal. And a controller's entire purpose in life is just to drive that error straight to zero. Moving on to section 2, anatomy of a PID. Let's slice right into the actual brain of this operation and see exactly how it processes that error. Now, what's really interesting about this slide is the continuous feedback loop you see happening here. Over on the left, you've got your reference. That's the set point we just talked about. It gets constantly compared to the actual output coming back from the sensor on the right. And boom, the difference between those two gives you your error. This error signal is then fed simultaneously into 3 distinct mathematical blocks: the proportional, integral, and derivative controllers, P, I, and D. Those 3 calculations get summed together to create one final master regulation command that tells the actuator exactly how hard to push or pull the system. It's just this constant, never-ending cycle of measuring, calculating, acting, and repeating. So let's break down those 3 letters because they're absolutely crucial. They represent 3 specific mathematical ways the controller calculates how to fix the error. First up, proportional gain, or KP. This looks at the present error. The bigger the error is right now, the harder it pushes. Simple enough, right? Next is integral gain, or KI. This looks at the past error. It basically accumulates all the past errors over time, giving the system a little nudge if it's consistently falling just a tiny bit short of the goal. And finally, derivative gain, KD. This one looks at the future error. It calculates the rate of change, like how fast are we actually closing the gap, and it acts like a brake to keep the system from just flying right past the set point. So you've got past, present, and future, all working together in perfect harmony. Now, if we pop the hood and look at the underlying math, we use something called the Laplace transform to view this in what's known as the S domain. The controller equation looks like this. U of S equals the proportional gain plus the integral gain divided by S plus the derivative gain multiplied by S, and all of that is multiplied by the error, E of S. Look, don't let the math intimidate you here. Even though it looks a bit abstract, this equation is literally just the mathematical translation of those past, present, and future concepts we just covered. And I promise we're going to ground this in a very physical reality really shortly. Which brings us to section 3, measuring system performance. Basically, how do we actually grade this digital brain and know if our carefully tuned P, I, and D gains are doing a good job?
When we visualize a system trying to reach its target over time, we grade it on a few key metrics. First, look at the rise time. That's how incredibly fast the system shoots up toward the goal. But notice how that line blasts right past the target at first? That is what we call overshoot. After that, it kind of bounces up and down until it finally stabilizes. The time that whole bouncing process takes is the settling time. And if it finally settles but never quite reaches that exact perfect target line, that frustrating little gap is the steady state error. Tuning a PID controller is basically this massive balancing act of tweaking those KP, KI, and KD numbers to get a super fast rise time without a massive overshoot and a quick settling time with absolutely zero steady state error. But here is a golden rule from the sources that you absolutely need to remember. Keep the controller as simple as possible. Seriously. The goal here is to use the PID to choose the exact response you want, but you don't always have to use all three elements. If a simple proportional controller totally does the job for your specific setup, just use it. Overcomplicating things with aggressive integral and derivative gains when you don't actually need them can just introduce instability and make your whole system jittery and unpredictable. All right, Section 4, the mass spring damper. This is the core of our explainer today. It is time to take all this abstract theory and finally put it to the test on a physical object. Okay, I want you to vividly imagine physically pushing a heavy block across a table. This is the classic mass spring damper problem. You've got a mass, M, sitting there on a surface. It's attached to a wall by a spring, which is K, and a damper. Think of it kind of like a shock absorber on a mountain bike, represented by B. We are actively applying a force, F, to move it a specific distance, X. This whole physical setup, that is what we call our plant system. It's the literal physical reality that our controller has to provide excitation to.
Now, since we happen to live in a universe governed by the laws of physics, we can describe exactly how this block moves using a dynamic model. The force, F, equals the mass times acceleration plus the damping coefficient times velocity plus the spring constant times distance. It's an incredibly elegant equation because it perfectly captures everything at once. The physical resistance of the spring wanting to snap back, the damper fiercely resisting any sudden fast movements, and just the sheer stubborn inertia of the heavy mass itself.
But to let our digital PID brain actually control this physical block, we have to get them speaking the exact same language. So we follow these logical steps. 1. Start with the dynamic model we just saw, which is in the time domain. 2. Take the Laplace transform. This is essentially a mathematical translator that converts our messy, complex calculus of time, velocity, and acceleration into really straightforward algebra in the S domain. And 3, from that algebra, we obtain what's known as the transfer function.
And that whole process gives us this final transfer function. X of s over f of s equals 1 over the quantity of mass times s squared plus damping times s plus the spring constant. I really want to stress this point. This equation is the block. It represents the total, real-world physical behavior of our mass, spring, and damper. But now it's in a format that our PID controller equation can plug directly into. Which leads us to the ultimate question for this example. How do our individual controller gains, KP, KI, and KD, actually contribute to obtaining our goal? Remember, our goal is moving this physical block precisely. Think about it dynamically. If you crank up the proportional gain, KP, you're hitting that block with way more force. That speeds up the rise time, sure, but that spring is probably going to cause it to bounce and overshoot the target. So what do? You increase the derivative gain, KD. This anticipates that spring's bounce and acts like an extra virtual damper, slowing the block down right as it nears the set point to completely kill that overshoot. And finally, the integral gain, KI. This guarantees that if the spring is stubbornly holding the block just 1 tiny millimeter away from the target, it quietly builds up enough extra force over time to push it exactly into place, totally wiping out any steady-state error. Honestly, it's like a beautiful mechanical ballet, completely orchestrated by math.
Bringing it all home with Section 5, Real-World Applications. The reality is, PID regulators provide absolutely exceptional control for the vast majority of industrial processes out there today. But you still have to match the right tool to your system's dynamics. As the sources point out, if you're dealing with a simple first-order system, say just heating up a giant tank of water, a simple PI controller is usually completely adequate. You probably don't even need the derivative part. If your dominant plant dynamics are second order, exactly like the mass spring damper we just analyzed,
well, full PID control is generally your perfect fit. However, if your process involves really long time delays, or maybe it has highly sensitive, lightly damped vibrational modes, standard PID alone might actually struggle, and you're going to need to look into more elaborate, advanced control strategies.
So, the next time you see a machine moving with total fluid grace, automatically adjusting to a gust of wind, or maintaining absolute perfection under extreme pressure, I want you to remember that continuous, calculating loop of past, present, and future happening right under the surface. I'll leave you with this provocative thought. If a PID controller is the hidden brain of automation, constantly calculating error and dynamically adjusting, what physical systems in your everyday life do you interact with that desperately need a smarter set of gains? Thanks so much for joining me on this explainer. Stay curious, keep analyzing, and we'll see you next time.